All right. Our final presentation has Elizabeth Lopez, Alexander Cash Loyacano, and Daniel DiStefano.
Hello, and thank you all for coming. I'm Alexander Loyacano,
I'm Elizabeth Lopez.
And I'm Daniel DiStefano.
and we're here to talk to you about the KE Power Shoe.
Okay. To walk around in public and not see most people on their phones is rather impractical since almost 90% of Americans have a cell phone. The average battery life for a cell phone is 10 to 14 hours, and that's with minimal use, like no social media, no internet, no calling.
On average, in the U.S. alone, over 2 billion pairs of shoes are sold per year, and the average person walks between 13 and 1,500 miles. Now, we use that on our average day. Why can't we take that energy we put forth to just go throughout and not use that to charge our phone, our iPads, our tablets, anything?
So we made the KE Power Shoe, which is a shoe that creates energy by walking with kinetic energy, and there's one battery per shoe. As you walk, it creates energy, which goes into the batteries, and in total, when you remove them and put them in the battery box, it equals 2,100 milliamps, which is the average amount for a portable charger.
We found 2 patents that were similar to ours, both involved a kinetic generator in a shoe, but one powered an LED in your shoe, and the other ended up powering a heating element in your sole, so as you walk, your feet are warm and they heats up.
To validate our product, we had multiple different questions to ask. Now, obviously, we had to ask how many people actually have a phone or other device they use. And 99% people said they did, for obvious reasons. Now, what kind of phone do they own really was a question we had to ask, because iPhones have different chargers than Androids, and maybe a Windows has a different charger along with non-smartphone devices. In the end, we went with a USB just so it's universal. Now, the age was also a factor, because what age do people start to get devices like this? And that's where we based the size of our shoe over there. It's about ages 10 to 12, which was about a size 4 boys. Now, if people would use this is rather important when you're marketing, and obviously 87% said they would.
Has your phone ever ran out of battery when you needed it? And majority of the people said yes. This graph shows how often does your phone die when you're away from home, and majority of the people said sometimes. So how great would it be for you to just be walking and then grab those batteries and then charge your phone when you're away from home? If you're like anywhere, like at a concert, if you're at a restaurant.
Okay, and how often do you use a phone in a day? Almost everyone were between 1 to 3 hours, but as you can see, there's a great majority of our audience that use it from 4 to 6, 7 to 9, or 10 plus, and this would benefit them greatly if they could charge their phone anytime they needed it from pretty much free power. And a lot of people we asked them, do you use your phone for school? And 81% of the people we asked said that they do use their phone for school, and this would be great benefit for them, because if you don't have your phone for like a big project for the internet, for information that you need to get for your project, then it's going to be kind of hard to get the information you need to complete it.
And so then we had to ask, how often do people charge their phone, and when, mainly? Overnight was a huge majority, but collectively, most people charge it once to twice a day. And so if you have to charge it once to twice a day, and you can do that just by walking, that's almost invaluable. And so how practical is this product if you don't walk very often? Well, most people walk between 2 to 4 miles a day, which is about school or work in general for most people.
Okay, and how long does your battery last? Most people answered between 7 to 9 hours, but that's like an optimal brand new battery, and that's not even like hours of straight use. That's kind of like on and off. And if your work day is longer than that, you're kind of short out of luck if it runs out of battery. So if you had just like a portable way to charge it, it would be almost invaluable. And how much would you pay for this item? A majority of our people said they would pay between $60 and $75, but some people even offered to go as much as over $100 or more, which would be phenomenal. And this was our decision-making matrix, and we had 6 different forms of our product, each one being powered by a wedge, a gear, or a lever, and that's pretty much just the power source to drive the coil or the magnet into the coils, which is free energy, and then it has to be stored within a capacitor or a battery, and it's just a matter of how much power you want to store. And our specific criteria, we had to break it down between safety, how comfortable it was, it had to be lightweight, it had to produce around 4 millivolts, it had to be waterproof, have easy accessibility, have good power storage, and be reliable. We rated everything on a scale of 5 to 1, 5 being the best, 1 being the worst. And throughout this test, we found that the wedge piston with a battery was the best option for us. And we defined safety as it does not catch on fire, it does not shock the user, and then how comfortable it was, it does not affect the walking motion, it's not painful to walk in or stand in. Lightweight, we wanted the whole system to be under 1 pound, and the power production, it has to produce more than 4 millivolts, it has to be waterproof, or the whole mechanism be inside a sealed container to where it is waterproof. Accessibility, the batteries have to be easily accessible. Repairs have to be, if they have to be made, they need to be easy to be done. And power storage has to store up to or more than 2100 milliamps. Reliability has to be durable. It won't crush under your body weight, and we want it to last around or more than a year.
Okay. The materials that we used metal rods. We used ABS plastic, which was from the 3D printer. We also used copper wire and neodymium magnets. In the actual circuit, we used multiple capacitors, inductors, diodes, and an 8-pin socket and a 5-boost converter. These are different drawings from the different stages before we started designing. These are the hand-drawn isometrics. These are the different cases that we tested, and the case that we ended up going with was this one right here. We were going to go with this case originally because the triangles were meant to disperse the weight of the user, and where there's a hole for the triangles was going to be where our pressure plate was going to be, which pushes the magnet through the coils.
In the end, we had to scrap that design simply because the triangles were not strong enough with the ABS plastic. So then we went with a solid wall and overhanging beams along with supports under them, but in the end, the beams would go in and the walls would collapse. And so finally, we just went with thicker, solid walls and minimal overhang. The only reason we had these is so it guides the incline on a horizontal motion, keeping everything nice and contained. Here's the initial and the final product. This one being much larger, even though it's a higher scale. It's just stronger, more sturdy, and a more reliable product. Here we have the stress test of the item in Inventor, and all the weight is right here under the heel of a shoe, which is where less pressure is applied because of the arch of someone's foot. And here we have the actual printed out product.
Okay, here we have the 3 different versions of our coil spacer. In the top left, we have the first original design. It was plain. It was just meant to keep the coils from snagging on the magnet as it went through. As we developed it some more, we added legs on it to keep the coils from being crushed between the case and to keep the coils on the actual case itself. And our third and final design is we kept the legs, we moved them farther to the end so the coils didn't slide off, and we added side guide rails to help the magnet work its way through and not get snagged up on anything, guaranteeing it. On here, we added support. This is one of our original case designs. We added support beams, which ended up not working that well. And then here, we tried a different design, moving where the coil would be in the middle and adding thicker walls. But again, we found out a better way to do it, and we ended up scrapping this design also. And here is one of our pressure plates. We ended up having a straight, flat edge on the front originally, but it didn't guide the force where we wanted to. So we added a rounder lip on it, which gave it more reliability and a better direction output for its constant motion it was in. And this is comparing the two edges, so you can see them side by side. And the one on the right, the final design we went with, we ended up making it longer so it could stick out of the shoe more.
Okay, so this shows that no stress was found on the pressure plate, which was really good. This shows that the direction that the force is applied. We test out both of these, and this was our original design, but we ended up going with this one because the sharp edges on this one were not working for us very well. This is a basic box that we first made for when we were starting off. And when we first printed it out, the magnet didn't go smoothly through the coil, so we had to sand it down. This just shows how we went from that box to lips being added to keep the magnet in place.
Here's the stress test we had for that in Inventor, and all the pressures right here, right under that arch of the foot, keeping it safer, more contained, and stronger in general.
Here we pretty much were just showing how, when the legs were on the table, how it actually lifted the whole system off, so the wires weren't getting crushed, so it made it more reliable. And then
When we were first putting the wires or the coils on around the box, we tested out multiple different wire. And when we tested out the red wire, we got volts ranging from 3.5 to 6 millivolts. And when we tested out the green one, we got 0 to 1.2 millivolts. So we went with this red wire. This shows our invention all set up. We added 3 springs from a pen right here. And then when we were making the incline, we embedded metal rods. And then we used the magnet's natural properties to hold it together.
here we have a picture of the whole mechanism put together. The lid is being held on by screws, but in our final product, we would have the top melted into place, so it created a more waterproof seal. And this is a bottom and top view, just emphasizing how the screws went all the way through to hold the lid on. And you can see the wires can snugly fit around the edge without being harmed in any way.
Okay, so this shows the magnet right here when force is not applied, like so when in between steps, and then this shows when you'd be taking a step that the magnet is pushed through the coils. This is a stress test to show that the way is dispersed where you want on the incline. This is a lid. Oh, sorry. The lid shows that most of the pressures take on the top of the lid because when we did the stress test, we put in 100 pounds for the weight. So this shows that the lid would save the components from being crushed or damaged in the process.
Here's the full exploded view in Inventor of all the pieces in its final assembly. This just shows how snugly they can fit, and they all have their designated area, the magnet within the coil spacer, the incline under the rails, and the pressure plate in its hole. Here we have the hollowed out view of the shoe. The problem we had here is there's cross hatches of rubber just under the comfort area, the sole of the shoe. And the problem we had there is we had to actually cut them by hand and sand it down to the thickness we needed it to be, which came out to be roughly this. Now, in a final product, we would have to raise the heel and the rubber just to keep it safe and comfortable.
Okay, this is the electronic part of the circuit that goes inside of the shoe. And this is where the input wires would be for the generator. And then this shows where the battery would be. This is basically the same circuit design for the circuit that goes inside of our battery box. This shows where our batteries would go. And then this is where the USB would be, so you could charge a smartphone. You could charge an Apple phone, Android phone. It's really universal. This shows why we use this chart to help us figure out why we chose AA batteries. And we chose AA batteries because they are less expensive and they are more common. But we also were considering going with C batteries because they can hold more electricity. But so do AA's because they hold 25 or 2,500 milliamps, which is the average amount for a portable charger. This shows photos of when we were testing our circuit with an oscilloscope. We found out that our product produced 3.8 volts, which is a pretty good amount of voltage. And this is our battery box. So once the batteries are charged, you take them out and you put them right here in this battery holder. And then right here is where you'd plug in your phone for the USB.
The final steps we'd have to take in developing this product is we'd have to make the case out of a stronger material, maybe a aluminum or maybe a carbon fiber. Customizing and printing out specific circuit boards so everything can fit where it needs to and we don't have to deal with solder bridges and other messy different processes. We'd have to make it more efficient so it can charge faster in fewer steps, so maybe it doesn't take an entire day or 3/4 of your day. Maybe it takes half or even less than that. We'd have to put a patent on it just so we can have this to ourselves and distribute it to where we think it needs to go. Finally, maybe reconsider C batteries. Although they are less common, they are more powerful.
We'd like to give a special thanks to our amazing instructors. Mr. Clement, our engineering design development instructor. Ms. Johnson, the introduction to engineering design instructor. Mr. Zoleds, our digital electronics instructor here. And our amazing mentors, Jeff Williams, who's president of Packer Engineering, Jesus Pineda, who just graduated from NIU in engineering, and Peter Demo, a manufacturing engineer, which is also one of our mentors.
These are the sources that we use for doing the research on our product and finding patents on it. And that's it.
Any question from the panel? Yes. No, that's why we had the removable AA batteries, just to prevent wires from going up the leg so it wouldn't get caught on any other material or it wouldn't get wrapped around the leg. The whole point of the AA batteries is just to remove them, put them in a separate case, which we actually have up here, and that allows it to be A, universal, and B, portable. It depended on how big your shoe is. If we did, maybe not, but there's only two things really found. One company was trying to do this with cattle, but they're having issues retrieving the separate power sources from the cattle. And then another one was a kid in India did something similar, but his relied on rotational motion, which we decided was too complicated. Just because if you have something that's spinning, it's more likely to break due to the centrifugal forces. And so just linear motion was what we went with because it was simple, easy, hard to break. In the beginning, it was between 13 and 1,500 miles. Yes. Yes. Well, if you're in the middle of a meeting and you don't have a wall outlet, it's being used by projectors or different other materials. During school, they kind of frown upon us using the outlets or the computers, as some people do. And so, well, we're allowed to use portable phones. We're not allowed to use the computers or the outlets.
So for this shoe, we made it specific for this size 4 kids, and it could handle 110 pounds. But if we did get a bigger shoe, the components in it would get bigger, and it could withstand more. So this was just an example for like a kid's shoe.
And that's also if when we said at the end, the next steps would be a stronger material, like the aluminum, which is light, or the carbon fiber. Those would be easier to use because we can make a mold or something like that. And even carbon fiber can be 3D printed now. The strength of those materials would be greater than this plastic, but for what we have, it would work if we had a shoe that wasn't cut in half. It relies on the heel of somebody's foot getting into contact with the ground. It would depend on how you run, if you run heel to toe or just on the balls of your feet. Specifically, I learned me and Dan learned designing the boxes and the different parts that the forces can be applied in a lot of different ways than standard flat planes. That's why we went with the rounded edge. Second thing is there's a lot of force on a small area, and dispersing that so it doesn't collapse upon itself is rather difficult.
One of the things I kind of learned was never overlook like the little things, like having the support pegs on this coil spacer. You never would realize how much the coils would move or how easily they get crushed and how much it could hurt you in the end if you don't realize that it happens. So kind of looking at all the little small things, making sure everything is concise and everything works perfectly, kind of emphasize on that and how important it is and how much you need to watch out for it.